Hi boys and girls, this is lecture 5.3, the title, Area. Before we begin to discuss area, we're going to need to describe a way of adding up sums of things. In particular, where area is concerned, we'll be adding up areas of smaller regions in order to approximate areas of larger regions. Something that we can use as a concise notation for sums is sigma notation. You may have seen something like this before. This sort of E shape is representing the sum of a number of terms. The sum of n terms, a sub 1, a sub 2, a sub 3, all the way up to a sub n, is written as, using the sigma notation, and then I equals 1 to n of a sub n. This is the thing that you're summing up, the term that you are adding up, and then this is telling you how many times to do it, from 1 to n. So this would be a sub 1 plus a sub 2 plus a sub 3 plus however many terms are in between up to the a sub n term. I is called the index of summation, and a sub I is the ith term of the sum, and the upper and lower bounds of summation are n and 1. Now let's see this in action because it makes a bit more sense when we are dealing with an actual term and actual numbers. In letter A, we're going to sum up the term I, where I starts at 1 and I ends at 6. So that means I becomes 1, then 2, then 3, then 4, then 5, then 6, and you add all of those things up. Here we are summing up the term I plus 1. That means, and we'll start at 0 to 5. That means that when I is 0, we'll have 0 plus 1, 1. When I is 1, then it will be 1 plus 1, which will be the term 2. When I is 2, 2 plus 1 gives us the term 3. When I is 3, 3 plus 1 gives us the term 4. When I is 4, 4 plus 1 gives us the term 5. And when I is 5, remember that's the last one that we need, 5 plus 1 is 6. And then you add all of those up for the sum of those terms. In letter C, we have j squared as the term that we're adding up, from j equals 3 to j equals 7, which will give us 3 squared plus 4 squared plus 5 squared plus 6 squared plus 7 squared. And that's how sigma notation works. On this slide, we have some useful summation formulas. The first one is just the term I. If we were adding up I a certain number of times from 1 to n, you know that's just going to be 1 plus 2 plus 3, etc., 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 and then we would add those numbers up. But what if n was something like 256? Would we really want to add 1 plus 2 plus 3 all the way up to 256? Or would we prefer this little shortcut, this little formula right here? It turns out that the sum of this term from 1 to n can be found by multiplying n times n plus 1 and dividing by 2, a useful shortcut for adding up that term. Here is another one for I squared. From 1 to some term n, 1 squared plus 2 squared plus 3 squared, etc. Again, if n was a small number, let's say 3, it wouldn't be such a big deal to list all of the terms and add them up. But if n were a larger number, let's say 14, I don't think we would necessarily want to calculate all of those terms and then add them up. Instead, how handy that someone has found a shortcut for us. If we take the n, multiply it by n plus 1, multiply it by 2n plus 1, and divide by 6, it turns out that that is the sum of this term from 1 to some specified n. Similarly, for I cubed, there is a sort of shortcut method here as well. Rather than listing all of the terms and adding them up, we can multiply n times n plus 1, divide by 2, and then square it. This is very similar to the first one. It is the first one squared, actually, so that might be an easy way to remember this third shortcut formula. These formulas are simple rules for working with sigma notation. If your term is just a constant, and basically you're adding up that number a specified number of times, let's say it's from 1 to 10, and your number here is a 2, then that's 2 plus 2 plus 2 plus 2 10 times. Well, obviously that sum is simply going to be n times the constant because you're simply adding that number up n times, then it will be n times c, the constant. Furthermore, if you have the sum of a term that is multiplied by a constant, you can bring that constant outside the summation notation, find the sum of your terms, and then multiply that answer by the constant. And finally, there is a sum and difference rule for summation notation. If you have a term that is a sum or a difference, you can separate that into a sum or difference of sums and find the result that way. Now let's do an example. We're going to evaluate a sum using our shortcut formulas as needed. In this case, the term that we're going to be summing up is I plus 1 over n squared. We're going to go from I equals 1 to n, and we're going to let n be 10, 100, 1,000, and 10,000. Now keep in mind that means we'd be adding up 10 terms, 100 terms, 1,000 terms, 10,000 terms. I don't think any of us wants to add up 10,000 terms, so we will be using our shortcut formulas along the way. First of all, though, let's see what it would look like if we were to list these terms and add them up. I would have the sum from I equals 1 to 10. We'll just use n equals 10 here, of I plus 1 over n squared. The first term, when I equals 1, would be 1 plus 1 over n squared, and in this case is 10, so that would be 10 squared. The second term, when I is 2, would be 2 plus 1 over 10 squared. The third term, when I is 3, 3 plus 1 over 10 squared, etc., until we got to the last term, when I is 10, so that would be 10 plus 1 over 10 squared. We would add each of those terms up and get the sum of this term from I equals 1 to 10. But there is a shorter way, and we're going to use our shortcut formulas to make this process a bit simpler. Remember that when there's a constant, we can pull it outside the summation notation. This n squared in the denominator is a 1 over n squared that can be pulled outside in just that way. 1 over n squared, now I equals 1 to n, we have left I plus 1. But remember, when there is a term that is a sum, we can rewrite that as a sum of sums. So this is now going to be 1 over n squared times the sum from I equals 1 to n of I plus the sum from I equals 1 to n of 1. Fortunately, we have some shortcut formulas we can use here. The shortcut formula for the sum of I from 1 to n is n plus 1 over 2. And of course, the shortcut for a constant is just to multiply it by n. So now this becomes 1 over n squared, and then we'll have n times n plus 1 over 2, which is the formula for the sum of I from 1 to n, plus 1 times n, which is n. Now, if I get a common denominator for this term by multiplying by 2 over 2 and distribute, I'm going to end up with 1 over n squared. This will become n squared plus n plus 2n all over 2. Combining like terms gives me 1 over n squared times n squared plus 3n over 2. And now I can distribute the 1 over n squared, and I'll end up with n squared plus 3n over 2n squared. One final simplification: if I pull an n out of the numerator and cancel it with one of the n's in the denominator, I have this simplified form: n plus 3 over 2n. And this will be the simplified form of the way to find the sum of this term from I to any n, which is much better than what we started with. All right, now that we have our beautifully elegant, simplified way of finding this sum, n plus 3 over 2n, let's calculate the sum for n equals 10, n equals 100, n equals 1,000, and n equals 10,000. Kind of amazing that we can find out the sum of 10,000 terms without actually adding up 10,000 things. So for n equals 10, we're going to have 10 plus 3 over 2 times 10, which is 13 over 20. For n equals 100, it's going to be 100 plus 3 over 2 times 100, which will be 103 over 200. And for n equals 1000, that's going to be 1000 plus 3 over 2 times 1000, which will be 1003 over 2000. And finally, for 10,000, we're going to have 10,000 plus 3 over 2 times 10,000, which will be 10,003 over 20,000. And that's how it's done, boys and girls. We're going to begin to discuss a way to determine the area of a plane region. And we're not talking about plane regions which already have formulas to calculate those areas, such as a circle or a rectangle or a triangle. We're talking about irregular plane regions and a way to approximate those areas. One way of approximating such a region would be the exhaustion method, and we're going to demonstrate that here by showing how to approximate the area of this circular region given here. Of course, we know what the area of a circle is, but we're going to pretend as though we don't have that formula. Instead, we have a way of finding the area of all sorts of polygons, just not a circle. So we're going to start with inscribing a pentagon inside this circle and saying we know the area of the pentagon, and we can say that that is an approximation of the area of the circle. It's not a great approximation. There's lots of space that's not accounted for, but it is an approximation. Furthermore, we have circumscribed a pentagon here as well. And knowing the area of that pentagon, we could also say that is an approximation of the area of the circle as well. Notice that the area of the pentagon would be slightly greater than the area of the circle, whereas the area of the pentagon that's inscribed in the circle would be an approximation slightly less than the area of the circle. But we know that between the area of the circumscribed pentagon and the area of the inscribed pentagon is the exact area of the circle. It has to be between that outer approximation and that inner approximation. Now notice here in the second figure, we've increased the number of sides. Now it's a hexagon, inscribed and circumscribed. Once again, an approximation of the area of the circle, in fact, a slightly better approximation. And once again, we know that the actual area of the circle would be somewhere between the area of the circumscribed hexagon and the inscribed hexagon. So we're getting closer to a good approximation of the area of the circle. Here, we've increased the number of sides again. We have inscribed and circumscribed octagons in this particular case. Notice that we're getting a much better approximation of the area of the circle as we increase the number of sides. And once again, the idea is that between the area of the circumscribed octagon and the area of the inscribed octagon is the actual area of the circle. Now imagine if we increase the number of sides, continue to increase the number of sides, drawing inscribed and circumscribed polygons with more and more sides. The approximation would get closer and closer. What if we let the number of sides go to infinity by using a limit? An infinite number of sides, of course, would represent the actual area of the circle. This method is a limiting process in which the area is squeezed between two polygons, one inscribed in the region and one circumscribed about the region. Using the limiting process would then take us to a place where if we could let the number of sides go to infinity, something that we can't actually do, but we can do using the limiting process in calculus, then we would be able to find the exact area of the circle as the number of sides goes to infinity. Continuing on with this idea, let's approximate the area of a plane region. Notice that we have a section of the graph under the curve y equals x squared plus 1 between the curve and the x-axis, and we're interested in the area of this region. Of course, it's not a regularly shaped region such as a circle, triangle, rectangle. This is something irregular. We don't have a formula that would automatically calculate the area of something like this, but we are interested in finding the area. One way that we could do this is to draw some sort of polygon inside the region to approximate the area. We're going to use rectangles. Notice that the interval is from 0 to 2. If I divide that interval into 4 rectangles of equal width, that means the width of each rectangle will be 1/2. Now the height of each rectangle will be a point on the curve, a function value at each of the designated x values. We can look at circumscribed rectangles and inscribed rectangles, and the way we get the heights of those rectangles will depend on which value we choose as the height of the rectangle. Notice that from the interval from 0 to 1/2, we have a function value at 0, which is 1, and we have a function value at 1/2, which is 1.25. Well, depending on which side of the interval we choose to make the rectangles will determine the height of the rectangle. If we choose for this particular situation the right-hand side of each interval, that will be the function value at 1/2, the function value at 1, the function value at 1.5, and the function value at 2. Those will be the heights of the rectangles that we choose. So for the left figure, our area can be calculated in this way. We're going to look at function values at 0.5, at 1, at 1.5, and 2. And those function values are 1.25, 2, 3.25, and 5. Since the width of each rectangle is 1/2, we can think of this combined area as the width 1/2 times the sum of all of the heights, 1.25 plus 2 plus 3.25 plus 5. Well, the sum of those heights is 11.5. So 1/2 of 11.5 ends up being 5.75. So using the circumscribed rectangles, we've approximated the area under this curve to be 5.75. Now let's use inscribed rectangles. To do this, we'll choose the leftmost point of each interval. For this first rectangle, we'll choose the height at the function value at 0, which is 1. And then for this second rectangle, we'll choose the height at 1/2. For the third rectangle, we'll choose the height at the left point of the interval, which is at 1, and that height is 2. And for the fourth rectangle, we'll choose the function value at 1.5, which is 3.25. So our x values now will be 0, 0.5, 1, and 1.5, giving us heights of rectangles at these function values, 1, 1.25, 2, and 3.25. Again, since the width of the rectangle is uniform, that's going to be 1/2 times each of the heights of the rectangles, which will be 1 plus 1.25 plus 2 plus 3.25. The sum of those heights is 7.5, and when we take half of 7.5, we end up with 3.75. So the combined area of the inscribed rectangles is 3.75. Now remember what we discussed before. The actual area under this curve must be somewhere between 5.75 and 3.75. The combined area of the circumscribed rectangles and the combined area of the inscribed rectangles. Notice here we have the same region that we were discussing before, but we've increased the number of circumscribed and inscribed rectangles. There are 8 circumscribed rectangles and 8 inscribed rectangles. Since we've taken the region from 0 to 2 and divided it into 8 rectangles, our width now is 1/4 for each of the rectangles. And the function values, of course, depend on which side of the interval that we choose. For the circumscribed rectangles, we're going to use the right side of each interval, which is at 0.25, 0.5, 0.75, 1, 1.25, 1.5, 1.75, and 2. In the interest of time, I went ahead and added the function values here. So these are the heights of each rectangle, and if the area then is the width, which is 1/4, times each of these heights, we can say that it's 1/4 times the sum of these heights, which is 20.75. So multiplying 1/4 times 20.75 gives us an approximation of 5.1875. That's a little bit better approximation of the actual area than when we were using 4 circumscribed rectangles. Now let's look at the inscribed rectangles. Once again, this means that we'll need to use the left endpoint of each interval. We'll need the function value at 0, at 0.25, at 0.5, 0.75, 1, 1.25, 1.5, and 1.75. The width of each rectangle, of course, is 1/4, and here are the function values at each of the endpoints of the intervals that we've chosen. The sum of these heights is 16.75. And if we say that the area is 1/4 times each of these heights, we can say it's 1/4 times the sum of all of them, which ends up being 4.1875. So the combined area of the inscribed rectangles is 4.1875, and the combined area of the circumscribed rectangles is 5.1875. Notice that this range between the two approximate areas is narrower than when we were using 4 rectangles. So imagine if we increase the number of rectangles, 16, 32, 64. You can see how these two approximate areas would get closer and closer to each other as we began to hone in on the actual area under the curve. So in this lecture, we have introduced the idea of using polygons to approximate the area under a curve. We have seen that using more polygons gives us a better approximation of that area. If we extend this idea into using the limiting process to allow the number of polygons to go to infinity, we then stand on the very threshold of one of the most amazing developments in mathematics ever. In subsequent lectures, we will discuss this idea further. It is so terrible of me to leave you in such suspense, boys and girls, so I advise you to tune in to the next lecture, and the next one, and the one after that as well. That's it for today's lecture. God bless you, boys and girls.